So there's two kinds of sequences I want to kind of make you aware of. The first one is called a geometric sequence. Here is an example of a geometric sequence. The terms are 6, 4, 8/3, 16/9, 32/27, etc., etc., etc. We'd like to find a formula for this, meaning we want to see if we can figure out like a function a sub n that's going to give us these terms. And again, I'm usually thinking, if no one's told me otherwise, that my first term is a sub 1, and then a sub 2, a sub 3, and so on and so forth. So what makes a geometric sequence unique or special is that each subsequent term can be achieved by multiplying the previous value by some number. And that's always the same number called the ratio. So in this example, what do I multiply by 6 to get 4? Well, the better question is, what's 4 divided by 6? So 6 times some number is equal to 4. Or in other words, the number we want is 4 divided by 6, which is 2/3. That's our ratio. That's what we're multiplying each term by to get the next term, right? 4 times 2/3 is 8/3. 8/3 times 2/3 is 16/9. 16/9 times 2/3 is 32/27. So our geometric sequence is going to look something like 2/3 to the nth power. But again, that's not quite all the story. Because if I start off playing n equal to 1, I'm not going to get 6. I'm going to get 2/3. So I need some other number out here so that it works out to be correct. So I need that if n equals 1, I need c times 2/3 to the first power equal to 6. Or multiplying both sides by 3/2, c is equal to 6 times 3/2, which becomes 3 times 3, which is 9. So the formula for this geometric sequence is 9 times 2/3 to the nth power. That's how we can find it if we're given the original thing. How did I know it was geometric? Well, I guessed. I was like, I think it's going to be geometric. And then I checked to make sure that every next term you're just getting by multiplying by 2/3. So if you think a series is geometric, you should be able to see that any next term divided by the previous term is equal to whatever that ratio is. Yeah.
Like 4 divided by 6, and it's
right.
got the answer, and then
right. Now I was able to stop there because I knew already it was geometric. If I was just trying to show it was geometric, or I thought it was geometric, I would probably check a couple more terms. Like 8/3 divided by 4. Oh yeah, that's also 2/3. And 16/9 divided by 8/3 is the same as 16/9 times 3/8. And yes, that reduces to 2/3. So every next term divided by each previous term should give you the same ratio if it's a geometric series. If you don't get that happening, then it's not geometric. Second question, or next question, what does this sequence converge to, if anything? So does this sequence converge? So our ratio, I think we're multiplying by each time, is 2/3. If you multiply a number by 2/3, does it get larger or smaller? Smaller. And if you keep multiplying by 2/3, you're going to get smaller and smaller and smaller and smaller until you get closer and closer and closer to 0. So the answer here is an emphatic yes. And the way we can say this, really, there's not a lot of work to show. If we say that we take the limit as n goes to infinity of 9 times 2/3 to the nth power, we're just going to say, well, yeah, since that number there, since 2/3 is less than 1 and not too negative, and bigger than -1, we can say that that part's going to go to 0. So we're going to get 9 times 0, which is 0. So I'll just point out if the ratio is between -1 and 1, then the sequence will converge and it will converge to 0. Nice. Let's look at a couple more examples. I'll try to remember the one that someone asked me about. So I want you all to try to find the pattern for this next one I'm about to write. So let's say our first term is -3, and then positive 9/2, -27/4, positive 81/8, -243/16. All I want you to do right now is just figure out what the ratio is. What are you multiplying each term by to get to the next term? So that's what you should all be doing right now. Well, knowing that it's geometric makes this a really short step. We're just going to take the second term and divide it by the first term. So our ratio, which we usually call lowercase r, is 9/2 divided by -3, which is the same as 9/2 times -1/3, which is 3/2 times -1, or -3/2. That's our ratio. So here's kind of a funky question. As we continue on in this sequence, do our terms get larger or smaller? Well, let me rephrase that. Do our terms get closer to 0, smaller, or further away from 0, larger? We're getting larger here, right? Every time we multiply by -3/2, the value gets bigger, even if it changes from positive to negative or negative to positive. We're still getting further and further away from 0 because we're multiplying by a number that's essentially bigger than 1 in absolute value. So our values are moving away from 0. So if we were to be asked to write, say, well, I suppose before I can write the limit, I better find the formula for the sequence. So here's one way to find the formula for the sequence. I'm going to say that my a sub n is equal to some number times -3/2 to the nth power. But I want a sub 1 to equal that number times -3/2 to the 1, which is going to be -3. So it looks like I probably need a positive 2 right there. So that 2 times -3/2 is equal to -3. So I'm thinking of my a sub n as 2 times -3/2 to the n. Let me show you another way to find it. No, do I really want to show you another way to find it? Not really. Yeah, I do. Sorry, I'm a liar. So here's another way you could go about this. You could say, well, I'm going to start with -3/2 to the n minus 1. Because if you plug in 1 there, what's -3/2 to the 0th power? What's anything to the 0th power? 1. So if you plug in n equal to 1 here, that's going to give you just 1, and then you can just put a -3 out in front. That's the same formula. It just looks a little different. If you want, you can think about this as -3 times, here things are going to get a little weird, -3/2 to the n divided by -3/2 to the 1. Right? If you divide those by each other, what do you do with the powers? You subtract them. Oh, n minus 1 is the n minus 1. And then you can multiply by negative 2/3, instead of dividing by negative 3/2, you get negative 3 times negative 2/3 times negative 3/2 to the n, which is the same thing we found here. That's positive 2 times negative 3/2 to the nth power. Neat. So I just want to point out there's lots of different ways to kind of find the formula for a sequence, and it kind of depends on how you feel about it. I kind of like doing it the first way I did it, but that's not the only way to do that. I will also mention that when you have a ratio that's negative, we often kind of break it up into two pieces, meaning instead of writing a sub n is equal to 2 times negative 3/2 to the nth power, we could rewrite this as 2 times negative 1 times positive 3/2 to the nth power, and then break it up as 2 times negative 1 to the n times 3/2 to the n. Is that necessary? Not really, but do people write it that way sometimes? Yes, they do. So now we can ask the question, what is this limit? What's this sequence doing as we go further and further out? Well, we said we were moving away from 0, but we're also bouncing back and forth between positive and negative. So we're going to be really positively large, and then negatively large, and then positively larger, then negatively larger, and then positively larger. We're going to get back and forth going closer to positive infinity every term, every other term, and closer to negative infinity every other term, meaning the limit's not going to exist. So here, the limit as n goes to infinity of 2 times negative 1 to the n times 3/2 to the n doesn't exist, because we're going back and forth between ever increasing positive and negative numbers. Just for comparison's sake, I'll point out that if our sequence instead was, say, something like just 2 times positive 3/2 to the n, the limit as n goes to infinity of that would still not exist. It's still not getting close to any specific number, but we would also say it doesn't exist, and we know it's getting really, really positively large. So we would say that the limit here is infinity. Still doesn't exist. We're just being more specific about the way in which it does not exist. This is a different sequence. I just was showing this one to contrast from that one. This one, you can't say it's positive or negative infinity because it's bouncing back and forth between positive and negative numbers. This one, you can say, yeah, it's getting really, really, really big, and it's always positive. So it's going towards infinity. Still doesn't exist. Questions about that? Okay. I'm trying to remember the question someone asked me. Let's see if I can find it here. It was this one. Sure. Okay. So, similar-ish question that somebody asked me about that I think is worth looking at. What about a sequence that is, I believe it was 2 pi to the nth power divided by 4 to the nth power? Well, I would prefer to write this in a different way. I would prefer to write this as 2 pi over n, sorry, 2 pi over 4, apologies. I don't want to write it as 2 pi over n to the nth power, or even you could reduce that fraction as pi over 2 to the nth power. So question, is our ratio, let's see some thumbs. Is our ratio larger than 1 or smaller than 1? Is that number inside the parentheses bigger than 1 or less than 1? Yeah, definitely bigger. I want some thumbs. I want more thumbs. Pi over 2, definitely bigger than 1, right? Pi is bigger than 3, so pi divided by 2 is certainly bigger than 1. So our ratio, pi over 2, is for sure bigger than 1, which means if you multiply by pi over 2, then pi over 2, then pi over 2, then pi over 2, if you keep doing that forever and ever and ever, the values get larger and larger and larger. Yeah, so we would say that this sequence has a limit that is also positive infinity. It's getting larger and larger and larger without bound. Okay. So before I stop talking about geometric sequences, has anybody in their class talked about a geometric series where you add up all the terms of the sequence? That looks like a no. Okay. We might circle back around to that near the end of the quarter because sometimes people will save that material to the very end. But for now, we will not. Oh, yeah, question. Series. So where you adding up all the terms. So yes, we're going to talk about other sequences. Yeah. But I'm just asking for this specific type of sequence, no one is adding up the numbers to get a value. Cool. Let me know if you do. The other type of sequence I wanted to briefly mention, although it might be kind of in a similar vein here as far as if people talk about it, but I do feel like kind of compelled to talk about it, are recursive sequences. A recursive sequence is a sequence where whatever the next term you're looking for is based on the value of the current term. So for example, we could say something like a sub n plus 1, the next term in the sequence is equal to 1/2 times a sub n plus 5. So when I'm thinking about this, I'm thinking, okay, a sub n is the current term, and a sub n plus 1 is the next term. With a recursive sequence, they have to give you a little bit more information. They also have to tell you what value you are starting at. So we're going to be given a beginning value of, say, a sub 1 equal to 3. So let's find some of the terms of this recursive sequence. So a sub 1 is 3, and a sub 2, the next term, should equal 1/2 times a sub 1 plus 5, which is 1/2 of 3 plus 5, which is 4. And then the next term, a sub 3, is going to be 1/2 times the previous term plus 5, which is 1/2 of 4 plus 5, which is 9 divided by 2, or if you prefer a decimal, 4.5. And you can keep going, right? The next term is 1/2 times the previous term, 4.5 plus 5, which is going to be 9.75. And you do one more, sure, one more, yeah. It's going to be 1/2 of 4.75 plus 5, which is going to be 9.8725, I think. Yeah. Right? Yeah, 0.25. Sorry, what? Sorry, let me just double check that math there. 8.875. There we go. That's better. All right. Not 9 though. Not 9.75 or 9.875. That should be a 4. Sometimes my 9s look like 4s. Sorry about that. Right. 1/2 of 4.5 plus 5 is 1/2 of 9.5, which is 4.75. And 1/2 of 9.75 is 4.875. So let me ask you all a question. If you had to guess, what would you guess these terms are getting closer and closer to? We went from 3 to 4 to 4.5 to 4 3/4 to 4.875. Feels like we're getting closer and closer to, I would guess 5. So the limit as n goes to infinity of a sub n certainly appears to be 5. So is it 5? Well, for recursive sequences, we have this idea of what's called a fixed point or an equilibrium, where if you plug that number in, you get the same value back. So let's just point out that if we plug in 5, so if a sub n is equal to 5, then a sub n plus 1 is going to be 1/2 times 5 plus 5, which is indeed 5. And the fixed points are the potential limit values. So since 5 is a fixed point, and since it seems like the numbers are getting closer and closer to 5, it's reasonable to say that, yeah, we think the limit of this sequence is 5. To say a little bit more about that, so to find the fixed points of a sequence, I will point out this idea is actually really important. This idea carries through kind of the whole 17A, B, and C series, talking about fixed points or equilibria of some sort of equation, because that's a lot of what the future things we're going to be doing are all about. It's like saying, oh, for this equilibrium, is it stable or unstable, and how do we find it, and. So this part is somewhat important. Yeah.
So the way to check if 5 is the value is by plugging 5.
Right, and so what we're actually, well, yes, but. Right, what we're actually do is we're gonna find the candidates first and then check to see where our sequence is getting close to. But yeah, that's the right idea. So how do we find a fixed point? Well, you want to find a value so that if you plug it in, you get the same thing back. So we're gonna say, we're gonna call them L, and we're just gonna set the equation in the following way. We're gonna set each a sub whatever, a sub n plus 1 equal to L. Equal, I can spell this. So in this equation, I would have said L equals 1/2 times L plus 5. So I'm trying to find a number that if I plug it in, I get the same thing back. And then we solve for L using algebra. So multiply both sides by 2. You get 2L equal to L plus 5. Subtract L from both sides. 2L minus L is going to be L equal to 5. Yep, there we go. It's our only candidate. So if the limit exists, this is the only potential value it could be. A couple words of caution here. Sometimes you're going to get more than one L value, right? You might get multiple fixed points, and not all of them can be the value of the limit if it exists. And sometimes you might get fixed points and none of them will be the limit value because the limit won't exist. So finding the fixed points is cool and it's kind of neat, but they don't tell the whole story. You kind of have to really look at some of the terms to get an idea of what's happening. Let's look at a couple more examples. Oh, yeah, that's a good one. All right, sure. Let's look at this next one. So here's our recursive sequence. Let's see, this is trying to number things occasionally here. That was a 4. This is a 5. So our sequence is defined by a sub n plus 1 is equal to the square root of 2 times a sub n. And we're starting with a sub 1 equal to 3. And I wrote 6 for some reason. Sorry. My brain got ahead of myself. So before we start seeing the first few terms, let's go ahead and just find the fixed points. So to find the fixed points, or point, it might just be 1. I don't know if there's more than 1 or not. We're just going to set L equal to the square root of 2 times L. By the way, the reason we're using the letter capital L is because we're thinking it might be the limit value. That's why they've made that choice. But you could literally call it anything you want. So what should I do to my equation to solve it? Take them in the square both sides. So I'm going to say that L squared is equal to the square root of 2L squared, which gives me L squared equal to 2L. And then if I subtract 2L from both sides, I get L squared minus 2L equal to 0. Oh, by the way, something I definitely don't want to do at this stage, I do not want to divide both sides by L. If I divide both sides by L, you wouldn't get a wrong answer, right? You get L equal to 2, but you don't get all the answers, right? I'm missing another solution. So even though that's not wrong, it's not what we want to do. We want to bring everything to one side, set it equal to 0, and then factor. So we get L times L minus 2 equal to 0. And then we get all the solutions. L equal to 0, or the other factor, L minus 2 equal to 0, meaning L equal to 2. So those are my fixed points. Those are the candidates for what the limit might end up being equal to, if it even exists. All right, so let's plug in our beginning value of 3. So our a sub 1 is 3, and our a sub 2 is the square root of 2 times 3, which is the square root of 6, which unfortunately we kind of need the calculator to deal with. So that's approximately 2.45. So I started with 3, and my next result was a little bit smaller. Let's see if that trend continues. By plugging in to find a sub 3, it's going to be the square root of, 2 times the square root of 6. And again, we really have to use a calculator here to get an idea of what that might be. Well, let's think about it this way. Do I want to think about it that way? No, not really. So that's approximately, well, what do I got here? 2.21. What I would kind of point out here is that if my number here is starting bigger than 2, then 2 times it, and then taking the square root is going to end up being smaller than the number I plugged in, right? If you have the square root of 2 times x, that's definitely going to be less than whatever x was, if x is bigger than 2. So this thing is always getting smaller because we started with a number bigger than 2. So if we do one more, although I don't think we really need to, it's kind of gross looking. It's the square root of that a sub 3 right there, which, oh, sorry, 2 times that a sub 3, which is the square root of 2 times the square root of 6, which is approximately 2.10. So it certainly seems like 2 is probably the limit here. So I think it's reasonable to say, yeah, the limit as n goes to infinity of a sub n is 2. It's not 0. And I would encourage you to check out what happens if we started a number less than 2. Going to get closer to 0 or closer to 2? I'll leave that to you to consider because I do think it's worth thinking about. So, yeah, kind of neat. I'll leave that one. You can work on it. Let's look at a couple more and then we will move along. So here's another recursive sequence. A sub n plus 1 is equal to 12 over 1 plus a sub n. And our beginning first value with a sub 1 is equal to 1. The numbers here are kind of not nice, which is unfortunate, but it's the way it goes sometimes. So let's go ahead and find our fixed points. Oh, 1 second here. Sorry, I didn't see you come in there. So I'm going to set L equal to 12 over 1 plus L. And if you might have noticed already, whenever I have an equation, I really wanted to not have fractions. So my first step is almost always to, if there is a fraction, to multiply both sides by the denominator. That's usually what I would do first every time. So I'm going to have L times 1 plus L equal to 12. Distributing the L on the left side, I get L plus L squared. And then subtracting 12, and then I switch the order to be like the more normal order. I've got L squared plus L minus 12 equal to 0. This does factors as L plus 4 times L minus 3. So my potential my fixed points are L equal to -4 and L equal to +3. And those are my potential limit values. And I will say, depending on where you start, each one of them could be a limit value, right? It might be that if you start at 1, you get one limit, and if you start somewhere else, you get the other value as the limit, depending on what we have going on. There really is more to say about that later, but now is not the right moment to talk about it. So the only other tool we have now is to just start plugging things in. So our a sub 2 is going to be 12 divided by 1 plus a sub 1, which is 1, which is 6. Our a sub 3 is going to be 12 divided by 1 plus a sub 2, which is 12/7, which is not particularly lovely. It's approximately 1.71. Keep going. Our a sub 4 is going to be 12 divided by 1 plus a sub 3, which is approximately 12 divided by 1 plus 1.71, which is approximately 4.42. So here's what I'm kind of seeing so far. We'll do some graphing, sure. I'm putting some n values on the x-axis and some output values on the y-axis. So when our first value was 1, our a sub 2 value was 6, our a sub 3 value was a little bigger than 1, our a sub 4 value is a little smaller than 6, it's 4.42. So it kind of looks like we're bouncing up and down, but maybe getting closer and closer to +3. Let's do one more. Our a sub 5 is approximately 12 over 1 plus 4.42, which is approximately 2.21. So we're over here now at 2.21. And if we do one more, I know I said one more before, but really one more this time, 12 over 1 plus 2.21. Well, just look at that. 1 plus 2.21 is 3.21, and 12 divided by 3 is 4, so it's going to be a little smaller than 4. It's going to be about 3.73. So definitely, to me, looks like we are zeroing in on the limit value of 3. We're getting closer and closer and closer to that value there. So I think in this situation, it's reasonable to say the limit as n goes to infinity of a sub n is positive 3. Neat. Okay, I think I have one more example I want to show you about this. Oh yeah, that one. So this next one is kind of, it feels disappointing. So prepare for disappointment. So here's our recursive sequence. A sub n plus 1 is equal to 4 divided by a sub n. And I'm not going to tell you the starting place yet. Let's just find the fixed points. So first, the fixed points. If we, well, set them each equal to L. So L equals 4 divided by L. So then multiply both sides by L. You get L squared equal to 4. And then our fixed points are going to be, so I will point out here, you could like subtract 4 and factor, but I think we can solve this without doing that and just get L equal to positive or negative 2. So those are our potential fixed points. Those are our fixed points. Those are our potential limit values. Right. So now let's look at the sequence and say we're going to start with a sub 1 equal to 1. So then my a sub 2 is going to be 4 divided by 1, which is 4. And my a sub 3 is going to be 4 divided by 4, which is 1. My a sub 4 is going to be 4 divided by 1, which is, I'm stuck in a loop. I'm bouncing back and forth between 4 and 1 and 4 and 1 and 4 and 1, and I'm never going to get out of it. So even though there are potential limit values, if the sequence starts at a sub 1 equal to 1, the limit's never going to exist. So here, if we write it this way, limit as n goes to infinity, you can just set that down right there. Yeah, perfect. Of a sub n does not exist. We're not getting closer and closer to either one of the potential limit values. And what's kind of interesting about this, I think, is that that's actually true no matter where we start, unless we start at one of the fixed points. So pick any number that's not 2 or negative 2. You can pick something like, I don't know, 7. Let's say we did a sub 1 equal to 7. That's a 1, by the way. So then a sub 2 is going to be 4 divided by 7. A sub 3 is going to be 4 divided by 7. But if we simplify that, that's 4 times 7 over 4, which is 7. And you can see we're back in the same loop. 7, 4 sevenths, 7. The next one's going to be 4 sevenths. So we're stuck. So no matter where we start, unless we start at 2 or negative 2, this limit isn't going to exist. You're going to keep oscillating or bouncing back and forth between whatever two values you have. Kind of funky. So this one also, limit as n goes to infinity of a sub n does not exist. All right, are we done with recursive sequences? I can say. Yeah. Cool. Before we depart from sequences, not that they're done with them forever, because certainly some of the ideas we've talked about with limits as something goes to infinity are still going to be present when we talk about limits. Are there other questions or concerns about? Well, there was someone asked something about like a negative 1 at the end in email, but it wasn't what the question was. But if there are any other questions about sequences, now is your moment to have them entertained. Yeah, no, we're ready to move on to the next stuff. Okay. So paper. Where am I putting all my papers? Here, that's what it is. Limits. But not just to infinity. Limits as some input approaches some particular value. So before I really say anything about limits, what I want you to hear is this. The idea of a limit is that we're just asking the question, what is the function getting really, really close to? What I should say, what value is the function getting really, really close to as x gets really, really close to some number? That's the whole idea. Specifically, we don't actually care what's happening at the number x is approaching. We care what's happening very, very close to that number. Let's look at an example. Let's say we have the following function. So the following piecewise function, f of x is equal to, sure, I like x cubed plus 1 when x is strictly less than 0. X plus 1 when x is greater than or equal to 0 and less than or equal to 2. And x squared plus 1 when x is strictly greater than 2. So we're going to graph that. For the x cubed plus 1 part, that just looks like your usual cubic function, but shifted up by 1. So we would, if we could plug in 0, we'd get the point 0, 1. So we're not quite getting that point. But then everywhere left of 0, it's going to look like your usual cubic kind of function like that. And then between 0 and 2, it's going to look like the line y equals x plus 1. So if I plug in 0, 0 plus 1 is 1. So I do actually get that open point to be a closed point now. And then if I plug in 2, 2 plus 1 is 3. There's that middle portion of the graph. And then to the right of 2, it's going to look like the graph of x squared plus 1. So x squared plus 1 is your usual parabola shifted up 1. So it would look like this. And then when we get to 2, 2 squared plus 1 is 5. So I would be starting kind of like here. And I'd have the usual parabolic shape. So there's the graph of this piecewise function. Let's ask some questions about limits here. So first question. What is the limit as x approaches 2 from the right-hand side of f of x? Or in other words, as x gets closer and closer and closer to 2 from the right-hand side of 2, what are my function values getting closer and closer? Let me do one more thing before I actually answer that question. Let me label these points or holes. This point here is the point, or this hole is the point 2, 5. This point is 2, 3. That one is 0, 1. Okay, I don't think I need to label that one. But those 2 points are kind of important because it's where we have a break. So if we approach 2 from the right-hand side, the function values are getting closer and closer and closer to positive 5. They're not actually going to get there, but they're going to get super duper close, right? For example, if you plugged in, say, like x equal to 2.001, then f of that x would be 2.001 squared plus 1, which is just a tiny, tiny bit bigger than 5. I don't know exactly what 2.001 squared is, but it's probably something like, I don't know, it's like 5.00 something. I know that's super helpful. But like, right, it's really close to 5. We don't actually get to 5 ever, right? 5 isn't in the range of this function at all, but that's not what the limit is concerned about. The limit is just asking, what are we getting close to? Oh, we're getting close to 5 as x moves in on 2. So this limit is equal to 5. I'm gonna write one more thing though. It's the limit as x approaches 2 from the right of x squared plus 1. Because that's how the function is defined when x is bigger than or right of 2. And then we can just plug it in and get 2 squared plus 1, which is indeed 5. Question.
Is the positive sign indicating that it's coming from the right?
Yes, exactly. I was just about to say, yeah. So the positive superscript there, the limit as x approaches 2 with a plus sign up there, means we're coming at 2 from the right side of 2, or the side of 2 that is bigger than 2.
Both of those negative.
Exactly. So to answer the next question, what is the limit as x approaches 2 from the left-hand side of f of x? Well, graphically, we can see that if we approach 2 from the left, the function values are getting closer and closer to what different number? What are the y values getting closer and closer to? 3, right? As x moves in on 2, we're moving up, 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 closer and closer and closer to the point 2, comma 3. We can also, though, just use the piece of the piecewise function that makes sense to use here. If we are just a little bit less than 2, that means we're using this middle piece here, because that's where x is less than 2. So we can replace this with the limit as x approaches 2 from the left of x plus 1. And you'll hear this a lot, probably, when you're evaluating a limit. If you can just plug in the value that x is approaching and get a real number result, that is almost always the correct answer. There are some rare exceptions, but we don't usually encounter those. So if I can plug in 2 for x, I get 2 plus 1, which is 3. So the limit as x approaches 2 from the left-hand side of this is 3. And then we would say that the limit as x approaches 2 does not exist. And the reason it doesn't exist is because the left-hand side limit and the right-hand side limit are not matching each other. For the limit to exist, the left and the right limit have to be the same. So this doesn't exist because the limit as x approaches 2 from the right side of f of x does not equal the limit as x approaches 2 from the left side of f of x. Terrible. Oh well, I'll live. So, what else do I want to say? Yeah.
How do you know which equation to use?
Excellent question. So, the way we know which equation to use is to think about what's defined to be what for particular aspect. So, if we're approaching 2 from the right, this means that x is larger than 2, but still close to 2. So that's why we're using this piece right here, because that's where x is larger than 2. On the other hand, for the limit as x approaches 2 from the left, that means x is less than 2. Now you might say, well, why don't we use the top part versus the middle part? Well, it's less, x is less than 2, but still close to 2, right? You can't be over here like -1 or -2 or negative. That's too far away. You have to be getting right up in 2's face. So we're getting closer and closer to 2 from the left using this middle piece of the piecewise function. And that's how we know. Cool. Let's see. No, that's good. So we could also ask the same sort of questions for what's happening at 0. So I'll point out that I think we can take this in down here. If we look at the limit as x approaches 0 from the left, well, then we're going to use the top piece of the piecewise function. Sorry, you can't quite see that. We're going to use the top piece because that's where x is less than 0. And again, I always remember that the left-hand limit is the less than side limit because they both start with L. So here we're using the piece where x is less than 0. That's going to be the x cubed plus 1 piece. We're going to plug in 0 for x and get 0 cubed plus 1, which is 1. I want you all to do this next part on your own. I want you to find the limit as x approaches 0 from the right of f of x, which is going to be the limit as x approaches 0 from the right. You have to decide which piece to use. Is it the top piece? Don't say the answer. You should write it down, whether you're using the top piece, the middle piece, or the bottom piece. If you're approaching 0 from the right-hand side or the bigger than side of 0. piece you should be using there is x plus 1, because that's where x is just to the right side of 0. Right there, where x is bigger than or equal to 0. And then we can plug in the 0, you get 0 plus 1, which is equal to 1. And since both the left-hand limit as x approaches 0 and the right-hand limit as x approaches 0 give us the same value, that means the limit exists. So this means that the limit as x approaches 0 overall, the two-sided limit of f of x is indeed equal to 1. So if the left and the right limit have the same value, then the overall limit is equal to that same value. All right. Okay. So I'll say this now. I'll wait to say that. So there's something I want to point out. What I want to point out here is, even though the function, when you plug in 0, you do get 1, that doesn't need to be true for the limit to exist. This limit does not care whatsoever what is actually happening at 0. Let's see another example to kind of emphasize this point. That one is short. Let's see this. So let's say, yeah, another piecewise function. It's going to be f of x equal to x plus 2 when x is less than or equal. Sorry, less than, not less than or equal to. Apologies. A strict less than 1. Yes, I can. F of x is equal to 7 when x is equal to 1, and f of x is equal to 4 minus x squared when x is strictly greater than 1. And again, we're going to graph it. You don't actually have to graph it to do it, but I like graphing it to see what's happening. So even though you could totally find the limit here without graphing, we still want to see the graph.
Does that middle one say 7?
That does say 7. 7's kind of fun. So let's let's graph. So here's the graph. Let's see, and we know important things are happening at 1. So when x is less than 1, the graph is going to look like y equals x plus 2, which is just a straight line. It's got a y-intercept at 2. And if we had the value of 1, 1 plus 2 would be 3, and we would get the point 1 comma 3. It's going to look like that. And I usually like to label those holes. And then when x is equal to 1, we're going to get a value of 7. So 4, 5, 6, 7. And then when x is greater than 1, we have the downward opening parabola 4 minus x squared. So it's going to look right. It would look like this. And it would come up, but actually it would go through the point 1 comma 3 and then have the usual kind of parabola shape going down, down, down forever. That happens to me too. So let's take a look. So just graphically, actually, here's what I want to say. This limit's going to exist as x approaches 1, because whether you approach 1 from the left-hand side or from the right-hand side, the y values are both getting closer and closer to the same y value, which is 3. Well, let's actually write it down. So the limit as x approaches 1 from the left of f of x, we will use the piece where x is less than 1, which is the x plus 2 part. We plug in 1, we get 1 plus 2, which is 3. We're not surprised. Looking at the limit as x approaches 1 from the right-hand side of f of x, we're going to use the piece of the function where x is larger than 1, which is 4 minus x squared. So that's going to be the limit as x approaches 1 from the right of 4 minus x squared. Again, we're just plugging the 1 in for x. I want to point out, even though we're approaching 1 from the right or from the left, you're plugging in actually 1, not 1.1, not 1.01, not 1.0001. You're plugging in 1, because that's how the limits work to get the value that we're getting close to. So that's going to be 4 minus 1 squared, which also is 3. And so overall, we can say, yes, the limit as x approaches 1 of f of x does exist, and it's equal to 3. Even though f of 1 is equal to 7. So what does this mean for us? Well, the limit exists because I'll say it probably 100 times. The limit doesn't care what is actually happening at x equal to 1. It cares what's happening really, 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 really close to 1. If you get really close to 1 from either side, you get super duper close to 3. You get like 2.9, 2.99999, right? Really, really close. What this does mean later on, though, is that since the limit exists and is 3, and the function at 1 exists and is not 3, the function isn't continuous when x is equal to 1. We'll define continuity later, but for now, you should just think about, oh yeah, if I tried to draw this without lifting my pencil off the paper, I wouldn't be able to. That's kind of a generic definition of continuity. If you can draw it and keeping your pencil on the paper the whole time, it's continuous. If you have to lift your pen or pencil off the paper to draw it, then it's not continuous. I keep reaching for water like it's there. Okay, so most of the time when you're actually dealing with limits, you're not going to graph them, right? It's more work than we really need to do. We could have done this without graphing it completely. So let's kind of talk more about just how to deal with limits in general. Yeah. So let's look at some examples here. Sure, you fit there, maybe. So, how to evaluate limits. Also, just as a side note, before we actually get to that, but first, how to read them correctly. So when someone writes this, I want to say 2 things. Thing 1, the way you read that is, I'm going to write the words. This reads as the limit as x approaches a of f of x is equal to L. Okay, we can read it. Great. I do encourage you to say all the words. They're all there for a reason. But more importantly, I would say, what does it mean? Well, the meaning is, again, the same meaning we've talked about so far. As x is getting closer and closer to a, as x gets close to a, f of x gets close to the value L. How close? As close as you want. Just not actually there, right? There has to be some minimal difference between the two, but that's the idea. Okay, that aside, how to evaluate limits? Well, first way is just by plugging in whatever x is approaching. So if you can just substitute in the number that x is getting closer to and get a real result, 99 times out of 100, that's going to be the answer. So here, the limit x approaches 2 is going to be 2 squared plus 3 times 2 plus 4, which is 4 plus 6 plus 4, which is 14. The only time this doesn't really work is like in the piecewise functions we dealt with. If we go back to that first example of the piecewise functions, if I said I was going to find the limit as x approaches 2 by just plugging 2 into this function, that wouldn't be correct. If I plugged in 2, I'd get 2 plus 1, which is 3. But the limit here isn't 3, the limit doesn't exist. So this idea of substituting in the value x is approaching doesn't work for funky things like this. And really, these piecewise functions are typically our main examples of functions that have limits that don't exist. So usually, if you just see something that's normally defined, if you can plug in x and get a value as the output, that's your limit. Let's look at some other examples. Say something like the limit as x approaches 1 of the cube root of x plus 7 plus e to the x minus 1 plus 2. And again, I don't see any problems with plugging in 1, so I'm just going to plug in 1 and get the cube root of 1 plus 7 plus e to the 1 minus 1 plus 2, which is going to be the cube root of 8 plus e to the 0 plus 2, which is 2 plus 1 plus 2, which is 5. Plus 2. Unsurprisingly, most of the time, this isn't going to be what you're going to see. You're not usually going to see a lot of limits where you just plug in, you get a number. I will point out one way that people, well, no, I'll do that in a second. So what you're more likely to see is a limit like this. Limit as x approaches 3 of x squared plus 4x minus 21 divided by x minus 3. And now if we try plugging in 3, you should always try plugging it in, even if you think something's going to happen. If we plug in 3, we're going to get 3 squared plus 4 times 3 minus 21 divided by 3 minus 3. And that's going to be 0 divided by 0. And what's 0 divided by 0? Good question. Literally, it could be anything. Let me show you what I mean by that. Because sometimes people are like, what do you mean anything? I really mean anything. Any answer will work. If I try to do 0 divided by 0 with long division, pick the answer you would like. I'm going to pick 19. What's 19 times 0? What's 0 minus 0? That works out, right? The remainder is 0. That's how division works, right? Not really, right? But right? I'm being a little facetious here, but the point is, you could have picked anything up there. 19 or a billion or -5, and all of them would have produced the same result. That when you did the division, you got a remainder of 0, which meant the division worked the way it was quote unquote supposed to. What that really means for us is when you see a 0 over 0, this is called an indeterminate form. That's just fancy words for it could be anything. And what it really, really means for us is you have to do more work. So when you see 0 over 0, that's what you should actually think is, oh, that symbol there, that 0 divided by 0, do more work. Every time. When you see 0 over 0, that's always what it means. You have to do something else. Usually that's going to mean some sort of algebraic manipulation. Not always, but a lot of the time. So here, if we look at this limit, I'm going to rewrite it as limit as x approaches 3 of, I'm going to factor the numerator as x. Well, I'm pretty sure there's an x minus 3 as a factor because I plugged in 3 and I got 0. The fundamental theorem of algebra says that if you plug in a number to a polynomial and you get 0, that x minus that number has to be a factor, which makes it easier to factor it. Right? If I know that plugging in 3 makes it 0, I know that x minus 3 is a factor, and then I know that the other factor has to be x first, so that x times x is x squared, and -3 times 7 is going to give me the -21. And that is how it factors, because the middle terms are going to be -3x plus 7x, which adds up to positive 4x, so we're good to go. So see, there's a reason why you actually want to plug in that 3, because it reminds you that x minus 3 gets to be a factor of the top part. Okay. So now what? Well, now we're going to cancel those x minus 3s, and here's why we're allowed to do that. If I plug in anything except for 3, if I plug in 4, for example, I get 1 times whatever this is divided by 1, and the 1's cancel. If I plug in 3.1, I get 0.1 divided by 0.1, and that thing is whatever it is. If I plug in 3.0000001, I'm going to get some tiny number divided by the same tiny number, which is going to divide to 1, and then you're going to be left with 3.00001 plus 7, which is 10.00001. So it looks an awful lot like we're getting closer and closer to 10. And we are. But we're allowed to cancel the x minus 3s here because the limit doesn't care what is happening at 3. And 3 is the only problem for those factors. And since the limit doesn't care what happens at 3, we get to just say it doesn't matter what those x minus 3s are. They're going to divide to 1. And then we take the limit as x approaches 3 of x plus 7. And all we're saying is that as x gets really super duper close to 3, this function, which is now this function, gets really super duper close to 10. Let's look at the graph. Because the graph is kind of neat, I think. You might think so too. You might not. I don't know. So here's what I point out. The graph is essentially y equals x plus 7. Except there's one problem. When you plug in 3, you don't get anything. So I'm going to graph y equals x squared plus 4x minus 21 divided by x minus 3. But I'm really just going to graph y equals x plus 7, and just remind myself that x isn't allowed to equal 3. So when I graph that, let's see, I've got a y-intercept of 7. I've got an x-intercept of -7. And my graph looks like that, where that's 3, and that's 10. And this is 0, 7. This is -7, 0. So everywhere this function, x squared plus 4x minus 29 over x minus 3, is the same as this function, except at that one point there, at the point 3, 10. Don't have it defined, whereas the actual line minus x plus 7 would. But that doesn't mean anything as far as the limit's concerned, right? As far as the limit's concerned, as x is getting closer and closer to 3, the function is getting closer and closer to 10. Same thing from the left or from the right. So I'll just say one more thing here. That yes, the limit as x approaches 3 of x squared plus 4x minus 21 divided by x minus 3 is equal to 10. And also, x squared minus 4x minus 21 over x minus 3 is undefined at x equal to 3. The limit still exists, even though the function isn't defined at 3. Because again, I'll say it one more time, the limit doesn't care what is happening exactly at 3. It just cares what is happening really, really close to 3. We'll also say this function is also not continuous at 3. Because although the limit exists, the function doesn't exist. So that's a problem when you're talking about continuity. Yeah.
So is it fair to assume that if you end up with 0 over 0, that it just doesn't exist at the value that you plugged in?
Correct. So it is definitely fair to assume that the function does not exist at whatever value you're plugging in. But I would say further, if you're getting 0 over 0, and we're talking about limits, it's also usually going to mean that the limit value probably does exist. Usually 0 over 0, not every time, but almost every time you get a 0 over 0, after some manipulation, you will get a real number value as your limit. Occasionally you don't because something else is happening, but most of the time you will. Let's see, what time is it? Okay, we got 15 minutes. We'll talk about the algebraic. So let's look at another example here. Yeah, we can do this one. Let's say we have the limit as x approaches 1 of 4x squared plus 5x minus 9 over 6x squared plus 7x minus 13. And if I plug in 1, I'm going to get 4 plus 5 minus 9 over 6 plus 7 minus 13, which, yep, 0 over 0. You don't have to write it out, but you should at least mentally check before you start just factoring at a problem that you do actually get 0 over 0 before you try to manipulate. Okay, this is where the thing I said before is actually really useful. We plugged in 1 and we got 0 in the numerator and the denominator. That means that in the numerator and the denominator, x minus 1 has to be a factor. So here's what happens. We rewrite the limit as x approaches 1 of, we know on top we have an x minus 1 times something. I think the something has to be a 4x here, so that 4x times x gives me 4x squared, and a plus 9 over there, so that -1 times 9 gives me -9. It's kind of nice, right? I'm not actually like thinking about the normal factoring where you're like, okay, I need something that multiplies to -36 and adds up to 5 and then do some weird, like, it's much, much easier to plug in the number. And then if you get 0, oh, x minus that number is a factor. That's great. Again, I will say that's only true if the original thing you're plugging into is a polynomial, right? If you've got like square roots or fractions or other things, that statement is no longer true. Did you have a question? Well, so if I plug in 1 for x here, what do I get? What's 1 minus 1? Right. But if it was 1 plus 1, I would get 2, which isn't 0. So it's always x minus the number that we plugged in. And on the bottom, we have also x minus 1. And you all finish off that last part there. Think about what you're going to have, something times x and then something else. I think it's got to be a 6x plus 13. No other choices. You can check if you want to. Like if you multiply this out, the middle term would be negative 6x plus 13x, which is exactly 7x. And on top, negative 4x plus 9x, which is exactly 5x. So it should work out, but you really, really don't even have to check. So then we get to say that those divide to 1. I like to write out one more step, although you could probably skip writing this step of 4x plus 9. The limit is x squared plus 1 of 4x plus 9 over 6x plus 13. And now I'm going to plug in the 1. I'm not going to write the limit anymore. So I'm doing what the thing tells me to do. I'm finding the limit, which is 4 times 1 plus 9 over 6 times 1 plus 13, which is 13 divided by 19. So as long as there's x's in your thing you're taking in the limit of, you still have to write the limit. But as soon as you've plugged in the value of 1 or whatever you're approaching, you no longer write the limit. You just are saying, oh, it's equal to whatever that number is. Yeah. See, how much time do we have? Okay. One more factoring example, and then we'll talk about a couple other things you can do. Let's say we wanted to find, well, let's change it up. Let's say the limit as x approaches -2 of x squared. Sorry, I have to think. X squared minus 5x minus 14 divided by x cubed plus 8. Once again, I'm not going to write it down this time, but if I plug it in, I'm pretty sure I'm going to get 0 over 0. On top, -2 squared is 4, minus 5 times -2 is 10, and 4 plus 10 is 14, minus 14 is 0. On the bottom, -2 cubed is -8, and -8 plus 8 is also 0. So this definitely is a 0 over 0 type. So we got polynomials. If you have polynomials, that means we're going to factor. I should say, we technically have a rational function, which is a polynomial divided by a polynomial. And since the top and the bottom are both polynomials, we're going to factor, since we know we can. We're still writing the limit as x approaches -2. The top should be relatively easy. So let me ask you all, think about it, don't say the answer. What should my factor be that's going to come out? If -2 made it 0, that means I should get x minus -2 or x plus 2. That's my factor there. And then the other factor on top is not too terrible. It's going to be x minus 7. Again, because x times x is x squared, and 2 times -7 is -14. On the bottom, it's a little trickier. We also have to have an x plus 2, but now we don't just have a quadratic, we have a cubic. There is a very straightforward way of factoring a sum or difference of cubes. So I'll point out that x cubed plus 8 is really x cubed plus 2 cubed. And the formula for factoring a difference of cubes, like a cubed plus b cubed, is a plus b times a squared minus a times b plus b squared. Or if you prefer, a cubed minus b cubed, a difference of cubes, factors as a minus b times a squared plus a times b plus b squared. There is an acronym for this. The acronym is SOAP. S for the same as a sign. If it's a plus here, it's a plus here. O for the opposite sign. If it's a plus here, it's a minus there. If it's a minus here, it's a plus there. And AP for always positive. So it's always an A, either plus or minus a B, and then an A squared, and an AB, and a B squared. When you find out the signs are SOAP. Same sign, opposite sign, always positive. Same sign, opposite sign, always positive. Kind of cool. I remember being really blown away when I learned that you could factor a sum of, like, I was like, yeah, you can factor a difference of squares or a difference of cubes or a difference of fourth powers or a difference of fifth powers. But for the odd powers, you can also factor a sum of cubes and a sum of fifth powers and a sum of seventh powers. It's kind of neat. It's not that important. So this right here is going to factor as x plus 2 times x squared minus 2 times x plus 2 squared. If you're not convinced, you can on your own multiply that out sometime and see that it does multiply out to be x cubed plus 8. And then we can divide x plus 2 by x plus 2. And last time I showed all the steps, this time I'm going to skip a step. I'm just going to go ahead and plug in the -2 for the remaining x's. So we get -2 minus 7 divided by -2 squared minus 2 times -2 plus 4. That's going to be -9 on top. 4 plus 4 plus 4 is 12, and that reduces to -3/4. But variety is the spice of life. There's lots of other types of 0/0 limits where we don't just factor. I will say, often, even if you're not going to start out factoring, usually at some point down the line, you end up factoring something. But let's look at a different example. Something like the limit as x approaches 2 of 3 minus the square root of x plus 7 divided by x minus 2. And now I'm unhappy. Because although if I plug in 2, I get 0/0 because 2 plus 7 is 9 and the square root of 9 is 3 and 3 minus 3 is 0 and 2 minus 2 is 0. I'm unhappy because I can't just factor that. It's not a polynomial on top. So I can't just try. How would I factor? I don't know how I factor that. So here, specifically when you have square roots in places, and it's a 0/0 type of limit, right? This is all in the context of 0/0 limits, right? Where you know, I'll point out, right? We've had all these 0/0 limits, and we've got lots of different answers. So I just want to reiterate that when you have a 0/0, the answer can be anything. That's why we call it an indeterminate form, because the answer is not yet determined until we do the work. For this type of 0/0, the usual process is to multiply the top and bottom by the conjugate of the square root part. So we're going to multiply both the top and bottom of 3 minus the square root of x plus 7 divided by x minus 2 by the conjugate of the square root part, meaning it's going to be multiplied by 3 plus the square root of x plus 7 divided by the same thing. Because we're only really allowed to multiply by 1, because that doesn't change the value. Here's the tip. When you're multiplying something by its conjugate, the things that are actually conjugates, you want to multiply them out. The things that are not conjugates, you don't want to multiply them out. Why not? Well, because we're looking to make that x minus 2 cancel, right? That x minus 2 is problematic. We would love for it to cancel and go away. Distributing or foiling up this bottom part is not going to help us see that. So leave the not conjugates alone, multiply the conjugates. Also, just to make sure everyone's on the same page, things are conjugates if it's essentially the same expression, but you've changed the sign from addition to subtraction or subtraction to addition. So I point out more broadly that a plus b and a minus b are conjugates. It's just the same expression, but you're connecting addition becomes subtraction or vice versa. Why do we multiply by a conjugate? Because it gets rid of the root or the radical. I will point out that when you multiply conjugates together, a plus b times a minus b, you end up getting a times a plus b times a plus a times negative b plus b times negative b. The middle terms add to 0. A times b minus a times b is 0. So you're left with a squared minus b squared. So a difference of squares factors as conjugates multiplied together, and conjugates multiplied together becomes a difference of squares. The reason I say this is because I really don't want to actually multiply out the top part. I don't want to show all that work. I want to just say, yeah, the top part is going to be 3 times 3 or 3 squared. The middle terms cancel. My 3 times the square root of x plus 7 and my negative square root of x plus 7 times 3 added to 0. And then I still have a negative square root of x plus 7 times positive square root of x plus 7. So I have negative square root of x plus 7 squared. Divided by, don't multiply out the bottom part here. X minus 2 times 3 plus the square root of x plus 7. Now we're going to simplify a bit. So on top we have 9. Okay, I'm about to make a mistake. Everybody watch the mistake I'm going to make. 9 minus x plus 7. I'll point out that that's a mistake, and here's how I know it's a mistake. Before, when I plugged in 2, what did I get on top? Like at the very beginning, when I plugged in 2, I got 3 minus 3, which was 0. If it's written this way and I plug in 2, I get 9 minus 2, which is 7, plus 7, which is 14. I didn't do anything that should have gotten rid of the 0 already. I haven't factored and canceled anything. All I did was multiply by something. I should still be getting 0 on top. And the reason it's a mistake is because I didn't write parentheses around the x plus 7. Right? It's 9 minus all of this. So that minus sign has to distribute to each of those terms. So just be careful. If you find yourself going from 0 over 0 to not 0 over 0 and you haven't canceled anything, it's probably some sort of mistake there. On the bottom, we still have x minus 2 times, what time is it? Yeah, I'm almost there. Cool. 3 plus the square root of x plus 7. We're going to simplify the top. So we're going to get the limit as x approaches 2 of 9 minus x minus 7 over the same thing. X plus x minus 2 times 3 plus the square root of x plus 7. And if we simplify the top, we have negative x and we have 9 minus 7, which is plus 2. So we have a negative x plus 2 over x minus 2 times 3 plus the square root of x plus 7. Oh, I made a mistake. What terrible mistake did I make? I mean, it's not that terrible, but it is terrible. It's worth a point, certainly. I didn't write the limit in this step. Right, I still have x's. I better still be writing the limit. The limit as x approaches 2. Oh, we're so close. Negative x plus 2 divided by x minus 2. Or, as you might think of it, 2 minus x divided by x minus 2. All right. Pick a small number that's not 2 in your head. Like 5 or 7, 9. 2 minus that number minus 2, they should be the opposite number. Like I picked 9, 2 minus 9 is negative 7, 9 minus 2 is positive 7, and negative 7 divided by positive 7 is negative 1. And that should have been true whether I picked 9 or 90,000 or 5 or negative 1. As long as you don't pick 2, the thing on top and the thing on the bottom are always opposite sign things. So if you subtract something and then subtract it in the opposite order, you end up just getting the negative of it. And when you divide them by each other, you get negative 1. So it's a long way of saying when you have something like this, you can just say that that's going to cancel down to negative 1. But if you don't like that, you could factor out a negative 1 from either the top or the bottom thing. So you could have also just rewritten this as the limit as x approaches 2 of negative 1 times x minus 2 over x minus 2 times 3 plus the square root of x plus 7. And then you can cancel the x minus 2's, leaving a negative 1 on top. Either way is totally fine. Now I've run out of room here and we're almost done. So I'm going to just plug in 2, even though it feels a little bit shady. So I get negative 1 on top, and I get 3 plus the square root of 2 plus 7 on the bottom, which is negative 1 over 3 plus 3, which is negative 1 over 6. All right, so there is more to say about limits next week.